Applications of trig derivatives. Let's say we want to determine the maximum and minimum value of this function y equals cos x plus sin x on the interval 0 to 2 pi. The first thing we're going to do is we're going to take the derivative. The derivative of cos is negative sine x, and the derivative of sine is cos x. Since we're looking for a maximum and a minimum, we're going to set this equal to 0. And rearrange to isolate the variable. At this point, I'm going to choose intentionally to divide by cos x because sin x over cos x is tan x, and that's usable to me, and cos x over cos x is just 1. And now I know that x must be pi over 4 because tan x of 1 is pi over 4, 45 degrees. Okay, so if we have a 45-degree angle, so this is my RAA, related acute angle of pi over 4, then a possibility for 1x is pi over 4. But it is also true, because I'm going over this whole interval all the way around this circle from all the way back to 2 pi, that this angle also exists. And x2 in this case is going to be 5 pi over 4. Okay, now we're just going to check to see which is the maximum and the minimums. So the smallest value of the function that I'm checking is f at 0. I also want to check f at pi over 4. I also want to check 5 pi over 4. And I also want to check 2 pi of my function. Okay, so cos x plus sin x, when x is 0, it's going to give me a 1 and a 0, which is going to give me 1. And let's do this one too. Cos of 2 pi plus sine of 2 pi gives me a 0 and a 1, so it also gives me a 1. Pi over 4, so I'm using my triangles here. Of sine is, or pi over 4 of cos is 1 over root 2 plus 1 over root 2. That's 2 over root 2. For 5 pi over 4, I'm thinking about being in this quadrant over here. Okay, so now I'm going to have the same numerical values, except sine and cos are both negative in this case. Okay, so now I'm going to look, see what my maximum values are and my minimum values are. This is my minimum, it's my only negative, and this is my maximum. Okay, let's try another problem. Okay, determine the maximum perimeter of a right triangle with a hypotenuse of 30 centimeters. So let's start by drawing a diagram. We'll say that's 30, and I know this is a right triangle. We're going to label the two sides, x and y. And I want to be able to talk about these sides in relation to the same thing. And the thing that they might have in common, that they share, is this theta here. So I'm going to write another definition of y. So sine theta is y over 30. So y is also 30 sine theta. And of x, so cos theta is x over 30. So x is also 30 sine theta. Now my perimeter is just 30 plus, sorry, I'm going to make a correction here. This needs to say sine, cos. 30 plus x plus y. So this is my perimeter. And I want to maximize this perimeter. So in order to do that, I'm going to take the derivative with respect to the angle. Okay, this constant drops away. Negative, or cos theta turns into negative sine theta. And sine theta turns into cos theta. And I'm going to set this to 0 to find the maximum. Just like in the last one, we set them equal to each other. Divide out the 30. So just like before, sine theta, did it again, sorry guys. Sine theta over cos theta equals 1, or tan theta equals 1. Theta equals pi over 4. And now that I know that, the angle that I'm going to get the maximum perimeter is pi over 4, now I can calculate what y will be when the angle is pi over 4. So that's going to be 30 over root 2. And x is going to be the same. Also 30 over root 2. So my total perimeter, which is what the question asked for, is 30 plus 30 over root 2 plus 30 over root 2. And if I just calculate that, I'm going to end up with 72.4 centimeters. Okay, let's try a word problem. A ladder that's 15 meters long leans against a wall. I'm going to start drawing my diagram. Here's my wall. Here's my ladder, 15. The top of the ladder is sliding down the wall at a rate of 4 meters per second. And it's going down. Find the rate of change of the angle between the ladder and the wall when the foot of the ladder is 9 meters from the wall. So this is the angle that I'm interested in finding. Okay, so this is a related rates. So I have two things that are happening here. I have the rate and then I have the positional values. So let's first talk about what I'm looking to maximize or minimize. So this is my goal. This change in the angle over time is what I'm looking for. So I'm going to need to find the derivative of theta with respect to time. So I know that I have a speed going down, but I don't actually know the height against this wall. So I'm going to start by creating a formula to find that. So cos of theta would be whatever the height of the ladder is against the wall over 15, which is always going to stay the same. So to rearrange that for the height against the wall is 15 cos theta. If I take the derivative of this, because I know this rate, this is dx dt, I will end up with negative 15 sine theta, and then I will have the derivative of whatever theta is, the rate of change of the angle. Now I can start plugging in numbers, so I know that the rate that the ladder is falling down the wall is 4 meters per second. I can also find this angle. So let's just do that on the side over here. So sine of the angle is opposite over hypotenuse, and in this case it'll be 9 over 15 at this point in time. And d theta dt is what I am looking for. Okay, when I rearrange to solve, sorry, this should not be here. Let's rewrite that. Cross out my 15s. The rate that the angle is changing with respect to time is -4/9. My units is radians per second. Okay, there's a bunch of homework problems for you to work on. Be sure to do them all and check your work.